Okay, so here is example 1 for class 21. It's a welding problem, and we're going to start off with problem 9.2, 9.6, 9.10, and it says 9.14. I don't know if that's in the next page. Oh, no, yeah, it is. Okay. So the first thing we want to do is understand what the welding condition is. Like, what does the weld look like? So we want to take a look at our welding symbol and understand what's taking place. What they want us to find is the allowable load, and we're going to start off with first using an allowable shear stress that they've provided of 25 KSI. So I'm going to redraw this so it can be a better explanation, because we're looking at a side view and it can't quite tell what that weld will look like. And I've exaggerated some thickness right here of the plate. And here's the whatever that thing is that's being welded to. And so we're applying a force right onto here, F, and the weld is going to be 5/16 high, and it's going to be a fillet right here. So right there to like right here, and if we were to look right, that height is 5/16. And I'll draw the rest of the weld right there. Looks like that. And there's also, because there's an arrow, this triangle is on both sides, that means that it's going to have also down here. So I kind of showing it onto the other side. And by that 5/16, we can infer, based on this table right here, that the from the weld height, that weld size of 5/16, that the plate is somewhere greater than 3/4 and up to 1 1/2 inches thick right here. So maybe it's like 1 inch thick, right? We can also know that not to exceed the thickness of the thinner part. That means that this guy right here, he's at least going to be 5/16 inch thick, right? So because this guy right here is the thicker part, is joined by this. We could probably use some other logic right there, but that's just an example of what this means. So to find the stress in this, we would use equation 9.3. Let me keep this and show you the configuration is the same as this right here. Let's see, can I undo any of these things? I'm looking at the undo the pencil. Yeah, I got to undo all of this. Anyway, I could do that later. Right here is the equation that we'll use right there, because that's the configuration. And you'll notice that 1.414, the 1.414, what it means is that we're actually within the throat section. Let's see, they're showing it right in here. This is where the discussion is, that we're taking a line through that section, right? So we're assuming this is a 45-degree angle right here, and we're actually going through and using this throat area. Right here you see the word throat, not the leg height, where this is H right here, that height. Here's the throat area that we're using. So that's where we get this 1.414. It's actually like, the cosine or the sine of 45 degrees. So that's why that's there. So we use the equation tau is equal, oops, I don't mean to do that. Go back into presentation mode. And I want to use black, right? Tau is equal to 1.414 times F and divided by HL. And so H is going to be the 5/16. The L is going to be the total length of this, right? And so since it's 2 inches on each side and it's welded in 2 spots, the total length is going to be 4. And they gave us the allowable right here, so we can go ahead and turn our stress into a limit, and then we could find that. So we plug the 25,000 in, and we don't know what F is. H is 0.3125, 5/16, and L is going to be 4, and we find we have an F limit condition of 22,100 pounds. Now we go down and we do 6 right here, right? 9-6, and we use electrode 1060. Oh, excuse me, 6010. A 6010 electrode. If we come up to this table right here, we don't use 60,000 psi, that's what the 60 ksi tensile strength. We go ahead and limit to an allowable stress, and so our guidance from the American Welding Society right here are based on a number of other things, but they also have a safety factor built in. So we already have, and we're limited to 18 KSI, right? So that's a pretty substantial safety factor already built in. Just a quick update onto this right here. There's also another method that we could use of using this F right here, and that F is like a simplified way. We would end up with the same results as what we're about to use, but instead we would have we find what a force per linear allowed inch of welding, and then so we could just add the thing up. So if we want to go backwards, this is sort of like a convenience type of method to do, but we're really calculating it the same way. So this was problem 9.2 here. So for problem 9.6, we set this instead, set it to 18,000 psi right here, and we have 1.414 F over 0.3125 and 4, and then we say F is now going to be equal to 15,900 pounds. Okay. Then we move on to problem 9.10. All right, so now what we've done is we have 1020 cold drawn steel, and I have to double check what happens here. Let me double check what the we go to 1020 cold drawn steel. Let's go to the back of Shigley here. So we're going to keep all that stuff, and let's go into the back of Shigley and look up cold drawn steel. And in our appendices, I think it's table A20. Find cold drawn steel, and a 1020 cold drawn steel. That's this guy right here. Here's cold drawn steel. We have an ultimate strength of 68 and a yield strength of 57 KSI. But we noticed that hot rolled, and I might have misspoken in a previous thing, and said I went from hot rolled into cold drawn. It's actually, by heating it, we get rid of the cold work, right? So that's that strain hardening, if you will, enhance of being cold drawn, makes this a stronger material than. Whoops, I didn't. The eraser doesn't actually work on this. Whoops, back. Come on, undo, baby. All right, you're just being annoying. I'll just leave it there. Okay. So anyway, so we started off with 68 in cold drawn, but by the heat affected zone turns the thing into hot rolled. So that means that its ultimate strength becomes 55 KSI. Yes, I have to write slower, I think. And so because we're using the material properties of hot roll now. Similarly, for the yield strength, it was, and I can't read it now, can I? I think it was 57 in the cold drawn. And now it converts down, it drops, it loses that work hardening and turns into 30. You get the idea. I don't know why I needed to draw that on there. So, so in problem 910, let's see, I wrote on that thing accidentally again. Problem 910, we need to adjust our strengths. So our tau allowable is, we have a couple different choices. First off, so we're coming back over to here. This is where we're basing this on. We're saying we're in shear and we use 30% of the ultimate, but you see the little cross thingy down here. It says shear stress based on metal should not exceed 40% of the yield. So we have to check both 30% of the ultimate, 40% of the yield, and we also need to make sure that we take that cold drawn and turn it into hot rolled in the vicinity of the heat affected zone. So we have to go either 30% of 55, which is 16.5 KSI, or the tau allow is 40% of the yield, which is 30, which turns out to be 12 KSI, right? All right, so obviously 12 is the controlling one, but it's not going to be the same stress that we have up here, right? Because this stress is based on what's inside the weld, right? So if I was just to look at one single triangle right here, that stress, once again, because of that's that 1.414 means this right here, that it's a smaller area, so has a larger stress. But in the welded material will fail in the shear along right here, or right here, right? So that's actually the stress here is going to be tau is equal to F over HL. So that 1411 is not in there. So what we would now calculate is to find tau is equal to F over HL, and we'll make that the allowable. So we'll say that it's going to be 12,000. It's going to be equal to F over 0.3125 times 4, and then F now is equal to 10,600 pounds. So that's what we say based on the materials, right? So we could be using the 60-10 and welding it to a 10-20 cold drawn steel that right around the heat affected zone, right? Because of the heating of the material around here, it loses all of its, like, and right, you can imagine even right there in that vicinity, it loses the heat, the cold working, and then drops its properties. And so we base it on yield based on this. And that's based on this recommendation. Again, that's by the American Welding Society, but here they're saying the AISC, American Society of Structural Construction, Steel Construction, I believe. I think it's American Institute for Steel Construction. Better look that up and double check what that says, okay? And once again, that's in the HAZ, the heat affected zone, where it loses its material, some material properties. Now, if we were going to instead now we look at problem 914, which is similar problem, except now you'll see that we have a different welding symbol. And what that welding symbol will mean, I'll draw this in 3D again. Is if we have a plate, and I didn't make that look see-through right here. What we will do is we will weld all the way around. And what does that mean? Well, we have this weld right here. That's the one that we expect, and still over here, right on the back side. of the thing. But we'll also have a weld that comes back and looking like this right here onto the side, and also underneath this, right? Because that's what that symbol means, all the way around. And we only need to have 1/2 of that thing, because we're saying that it's welded all the way around. So it actually has a weld on all 4 sides. And this is actually pretty good practice, especially on ships, because on the other one, there's actually ways that moisture can actually get inside in between here and cause corrosion where you can't access it, you can't chip it and paint it and coat it and do anything about the weld, about the corrosion that's on the inside. But here, we've pretty much sealed the thing off. So we're preventing that. So most of the time on a ship, we'd actually want to do this all the way around. So let's see, and they're saying now they want to find the maximum stress. So we're given the force that's on there. So we say tau is going to be 1.414 F divided by HL. 1.414 40,000 and divide it by 0.3125, and now we're going to have 2, 4, 6, 8. We're going to have 8 inches total of weld. So that's going to come out to 22,600 or 22.6 KSI. And so then we should choose the electrode based on the strength. And I say next page, but I don't see my next page as part of this. Let's say. Okay, I see. All right, so here you go. I reroute this page right here. So now, if we were to use out this, we could make it an additional safety factor. That's what I want to do. So I'm going to come up with a new safety factor. Now this, by the way, this allowable that we have up here already has a safety factor built into it, right? It already has a safety factor right here. So if we use 60-10, I wrote 60-61, I meant 60-10 electrode, we find a new safety factor of tau allow over actual tau. We're actual. We'd see they get 18.0 divided by 22.6, and that's 0.8 is no good. And then if we did 70-18, we're obviously, it's going to be more here. No, not necessarily, yeah. The tau allow, I don't need to write this actually, okay, is going to be 21 divided by 22.6 and also 0.93, and that's no good. So for this, we would want to use an 80 series. I don't know, probably you could find an 80-10 or an 80-18 or an 80-11. Just depends what something's common. I'm not quite sure what the common electrodes are. I'm using these because I know they're common electrodes. And we just take, that's going to be 24 divided by 22.6. And so we get 1.06 and okay. So we don't know, right? This is the study of safety factors. We don't know what the other things could be in. We don't know what safety factors were applied with that 18 KSI limit. That was simply because of the weld, not because of the application. So it depends. What is this for? Is it for supporting human life? Is this a bracket and this is somehow supporting something in a roller coaster? right? And does it have to survive corrosion? Does it have vibration issues? Is there going to be fatigue involved? Is there a dynamics loading? And then most of all, I mentioned already, is human life dependent on this? If this thing breaks, will people die? Well, that 1.06 would have to be defended in a court of law. So it depends on what the application is. Don't depend on somebody else's safety factor. You need to dig deeper into it. So that's it for the example. And I'll keep it because I'm going to get rid of it here. But class is going to start in, let's see, about 35 minutes. So we can keep on going right here. Let me disconnect this. And bonus features is a little bit of guitar. Okay, so let me see. I'll go camera, and turn the camera on. Is it gonna come back on here? Look, there it is. All right, so we're wearing the college shirt, right? It's supposed to be sarcasm because it's like, you know, what college? Just generic college. Any college, who cares? They're all just one shirt's different than another. So right here we have a Gibson Midtown. It looks a lot like the 335. It's with the it has the same kind of a general look to a Les Paul Custom, where we have, of course, we have the humbuckers. We have covers. I like covered humbuckers. We have block inlays right in there, and we also have the diamond headstock, but it also has the triple binding. I really like the triple binding. I'm a Gibbs snob. That's the joke, right? I don't like the cheaper versions of this from other companies. There's also Epiphone, which used to be its own company, but it was a subsidiary kind of Gibson. And this has nice, actually, I think I have a Van Halen brand pickup into the bridge pickup in this. But this is definitely a like blues rock kind of guitar. It has a lot of, I really like the overall kind of blend between a 335, which is more of a bluesy guitar. Yeah, you can play it rock. There's a lot of rock musicians have played ES 335s. Because of the way the body is, this is actually carved out. This is like a solid piece of mahogany, and then they carve out all the routes, and then they put a maple cap on top of it. So instead of like a ES335 is really a two-part, like a top and a bottom, and then some like a ring kind of side to it, and then it has a center block of a different, I think it's maple. I think it is. It's got a center block that's to prevent feedback. So it's not actually a hollow guitar. And this one, similarly, is not completely hollow. If you reach your finger in there, you could feel that there is I'm going the wrong direction. You could feel there is a center block to it, but now it's like more of a mostly mahogany construction. So it's a lot like a Les Paul. And so what we have, let's see. Do I have it turned off? Is that why it's not making noises? Yeah. Now the big trouble with the Gibson and this headstock is this G string right here, right? So that's it goes down and over and this way, and so it gets hung up right here at the nut. There's a little friction that takes place. So when you bend something, it often goes out of tune. You can hear that knocking. So what you get, you can push it right there. I'm so addicted to tuners that now it becomes very difficult to tune by ear. I hear, especially when someone's paying attention. Also, with the change of seasons, the wood absorbs moisture, and the temperature also affects it. Also, on Les Pauls and a lot of Gibsons, the fret's fairly tall, and you can change the tune. You can put out a tune by pressing down too hard. See, but there's out of tune. You have to have a relatively light touch. Nice guitar all around, right? So you can have like a nice, pleasant stuff too, especially with the neck pickup. Get it to what's going on here? It's not something wrong with that switch. There you go. More guitar stuff. It's black too. It's one of my favorite color for guitar. So it's a pretty good. This is a nice guitar. I like this one. I like the 335 probably better. It's got more mojo to it. But this was this was not that expensive. Well, relatively speaking, it was probably like a $1,500 guitar as opposed to 335. It's now like a $3,000 or $3,500 guitar. So anyway, that was that. And so that's another video down the drain, down the hatch, in the can. One of those words. Done.